welcome to our nanocatalysis lecture. First of all, I would like to thank you for your understanding. I'm really sorry that I cannot join you today for the lecture in person, but don't worry. I prepared something special so that to ensure that we don't miss out any important content. So today, in place of our traditional live lecture, I will be providing with you with a recording of our lecture from 2021. So in that course or on that year, I covered exactly the same content, and the concepts, the examples, and the insights are just as relevant today. And I am very confident that you will enjoy, and then you will find it that it's valuable. Well, even though the video recording or the video lecture is not the same as being together in person in the classroom, I hope that this recording or this video lecture can capture the excitement and energy that nanocatalysis brings to the table. So please take your time to watch the video lecture carefully. Feel free to pause, rewind, rewatch any sections that you need. And as always, I am here to support your learning. So if you have any questions or any clarifications that you need after watching the lecture, feel free to contact me and reach out by email, for example, or come to my office, or we can discuss also during our next live lecture as well. So this is it. With this, I finish this my introduction, and then I will give you the floor for our video lecture that we will continue the discussions on the synthesis of nanocatalytic materials, focusing first on the synthesis of the support, and then going for the synthesis of the metal nanoparticles, or the active phase that comprise the nanocatalyst itself. So enjoy the lecture, and I look forward to further discussions, and I look forward to be there in person for our next lecture. Please let me know. So in our last class, in the last set of lectures, I should say, we have covered a lot of subjects, and then we started the discussion last time on the synthesis of nanocatalysts. And this is the point from which we will start our lecture today. So we will continue and move forward towards the discussion on the synthesis of nanocatalytic materials, focusing more on nanocatalysts that are comprised of nanoparticles that represent the active phase deposited at the surface of a support material. So we will approach the synthesis, describing the synthesis of support materials. Then we will move towards the synthesis of the nanoparticles of the active phase. And then we will also cover and mention strategies that involve shaping of the catalytic or nanocatalytic material into macroscopic bodies that, for example, are used for fixed bed applications in industry. Okay, so we started in the last lecture the discussion on the synthesis of support materials. So we started by discussing disordered mesoporous oxides such as silica, alumina, titania, for example, in which in these support materials, they are comprised of primary particles. There are a few nanometers in size, so we can see these primary particles here on the support.
And these primary particles are aggregated or joined together, forming micro-sized secondary particles. So several important materials or supports have this kind of morphology, this disordered mesoporous structure in which the porosity is defined by the interparticle distances here in the support. They are widely used and interesting because they have low cost to make this kind of materials. They are robust from the mechanical point of view, and also they are very easy to make. And the syntheses are usually focused on wet chemical methods, such as precipitation from an aqueous precursor solution, such as the sol gel synthesis that we discussed um, last class, or hydrothermal methods, and also gas phase synthesis, such as flame hydrolysis, which we also discussed last time. So in addition to these disorder systems, there are also support that comprised ordered porous structures, such as mesoporous silica, for example, which has the pores organized into one or more dimensions along the structure. So here we can see the clear morphology of these one-dimensional pores. And here we have a cross-section showing this hexagonal arrangement having the porous structure. So this kind of synthesis is based on the utilization of surfactants in the reaction mixture in which the formation of silica takes place. So when we have some surfactant molecules above a critical concentration, they form micelles. And then even if we increase the concentration, or we can control this concentration, these micelles further evolved into rod structures, which can be further assembled into an hexagonal array of micellar rods. And this hexagonal array of micellar rods can be employed as templates for the deposition of silica at their surface. So after silica is deposited at the surface, like we can do like some drying to remove these surfactant molecules that act as the template. So we end up with a morphology that resembles the shape of the template that it was used to form the silica. So we end up with ordered mesoporous silica, which is exactly what we see in this image. We can see this hexagonal arrangement of the silica that replicates the shape of the hexagonal packing arrangement of the micelles that were employed for the synthesis. And also, additional types of functionalizations can also be employed by this method, in which we can further function. So here, for example, we have this silica deposition at the surface of this hexagonal array of micellar rods, so, which after the removal of the templates or a copolymer here in this case can lead to the formation of the mesoporous silica. But we can also add molecules to this synthesis, or use this play with the composition of these additives and copolymers here in this case, so that we can add some specific functionalization into the inner walls of these mesoporous silica, and this can be used to further control or give extra functionality for catalytic applications. So another class of ordered porous materials that play a very important role in nanocatalysis are zeolites. And zeolites now comprised order microporous materials. So the sizes of the pores are much smaller or are smaller relative to the mesoporous silica that we just saw. So zeolites are ordered microporous materials. They are aluminosilicates that occur, they are very abundant in nature, and therefore they have been known from several centuries already. And they are used widely in catalysis, and they are produced actually industrially and on a large scale. So why we mentioned here that these systems are microporous? So you can see that they have the pore sizes for zeolites are around 1.5 nanometer only. So they have pore sizes of around 1.5 nanometers, and they typically consist of aluminosilicates in their composition, which means that they have high affinity for the uptake of water. And regarding the synthesis, they are normally synthesized hydrothermally from precursors. And these precursors can be amorphous aluminosilicates or metal organic precursor molecules in which precipitation and condensation reactions occur that are followed by drying. So hydrothermal synthesis is just heating an aqueous solution containing the precursors to initiate reactions that will lead to the desired material. So here is an example of a synthetic strategy for the synthesis of the zeolite. So it's an aluminosilicate. So it has a precursor that contains silica, a precursor that contains alumina, water. It has some cation source that we will see how this is important as well. And then also a structure directing agent, in which this structure directing agent also acts as templates to dictate the porous structure. So these precursors, for example, so they are added into a reactor system in which the hydrothermal conditions will take place. So in this case, it's a sealed autoclave over 100 degrees Celsius in temperature at high pH. And then after heating, we have this condensation, reactions, polycondensation, and precipitation taking place, leading to the formation of the crystalline zeolite, in which the structure directing agent helps or acts as templated during the synthesis procedure to dictate the porous structure. And then after filtration, we get the solid product, which is the desired zeolite. So I'm sorry, there was some error here in this slide. I don't know why is this way, but I will correct this for posting afterwards in the Moodle. So I'm sorry for that. I don't know what happened. Okay, so in this case, during the synthesis, the porosity of the zeolites, which is important here, because we are talking about these materials as being the supports in catalysis. So also, like in the case of the mesoporous silica and also the zeolites, sometimes only the supports functionalized can be already the nanocatalyst as well, but these systems can also be functionalized with or have nanoparticles deposited over their surface to generate the desired nanocatalytic material. So regarding the porosity of zeolites, the porosity is induced by the presence of templates in solution. So these templates can consist of ions, small molecules and ion pairs. So these templates can direct then or induce the formation of the porous structure or dictate the crystalline phase that will be formed and therefore generate the desired porous structure. And in zeolites, the primary building block of the zeolite structure is this tetrahedral unit in which we have a metal cation, usually silicium 4 plus, surrounded by 4 oxygen anions. So it's usually this unit which acts as a building block. So this tetrahedral unit is shown by here by these two representative images, because you see in the literature the structure of the zeolites are usually described or discussed as being formed by the interconnectivity between these different tetrahedron building blocks, as we will see very soon. So these building units or these tetrahedra can be connected in different ways to form three-dimensional larger structures that share corners, edges, or planes between each one of these individual tetrahedrons, for example. And by combining these primary building blocks, secondary building blocks, much larger, can be constructed, such as like having 4 or 6 rings of species containing these connected building blocks. So here is one example in which, so this is an example of the modernite, which is one type of zeolite. So this image is actually very, very clear, and this was taken from Wikipedia actually. So it was very nice that I found this there. So we have these individual SeO4 building units, so these tetrahedrons, shown in 2 ways here. So you see that in the structure, it's shown by this representation is used here in the structure. So these building blocks can be organized into secondary building units. So they interconnect, like sharing corners here in this case. And these secondary building units can be even further connected themselves with other secondary building units to generate the final structure of the zeolite, as shown here in this image. And then the crystallization of, or the organization generated by the organization of the secondary building blocks. So this leads to the final crystal structure of the zeolite, and this leads to the formation of well-defined pores in the structure of the zeolite, as shown here. So these pores are formed and dictated by the crystalline structure of the zeolite that we have. So these larger units can be arranged in a lot of different ways, like generating different geometries. And one example of these final geometries that are obtained is this sodalite cage, which is very, very common in the description of the zeolites. And these cages can then be further organized into 3 dimensions, generating cavities, channels, and cages or pore in the structure. So here is another example of this sodalite cage. So it's represented as a cage here. So it's a different way of representing, but it's the same structure. So here you can see the location of aluminum, silicium, and oxygen atoms For example, and here we have the representation of the structure in which we have the pores here, for example, by the organization of this structure into the 3 dimensions. And then for this specific type of cage, for example, it can be organized into different ways, for example, generating different crystalline structures that we will have a different porous structure, as also shown in this image. So we have, from the synthesis, we have like silicate or aluminosilicate oligomers that work as the precursors. Then we have hydrothermal treatment, in which we have condensation and growth reaction, generating the crystalline structure here, the arrangement into these structural building blocks, which is the sodalite cage, which is obtained by the organization of these tetrahedral building units, and these can be further organized into 3 dimensions, into different arrangements, leading to different zeolite structures. And here is another example of these representations of these kinds of structures. So also, I would like to show you that, of course, it's very important to see these structures and to be able to interact with them. And then sometimes it's difficult to see this on the static slide as I was showing you. So I would like also to show you this website, which is called here chemtube3d.com. So here, if you go to the menu here, you can see that they have a lot of interactive 3D structures for several types of materials, and then we have here, for example, we can come to framework structures in which there is the representation of several types of zeolites, for example. So this is very interesting because it's an excellent resource for visualization and understanding of these structures. So, for example, taking a look at this, at the structure of this zeolite as an example, so we can see here the structure. So we have here two types of zeolites, the zeolite X and the zeolite as ZSM5. So here we have only the SeO4 tetrahedra structures shown that form the framework for clarity. But here we can see, we can play around if we want here in this material. And then, for example, here we can turn and look. It makes it very nice. And then we can take a look at other zeolite structure as well. And then here we can have like highlight. So here in this zeolite, we have silica tetrahedra and also aluminum tetrahedra, because this is aluminosilicate, right? So we can highlight the silicon tetrahedra, highlight the aluminum tetrahedra, and be able to see like the porous structure of the zeolite, right? Like right here. Okay, so this website can be an excellent resource for checking this zeolite structure. So I will post this on the website as well on Moodle, and so please, I will put some homework exercises that involve checking these structures in 3 dimensions for you guys to get familiarized with this. So let me see, let me come back here to my PowerPoint. Let's see if it works. Yes, hopefully these illustrations and changes were smooth on Zoom. So even though, as we discussed, the structure of the okay, so getting back to the discussion of the zeolites, the size of the pores, whether they are straight channels or if they are cages or cavities, the size of the pores is determined by the crystalline structure, and therefore, which means that they are determined by the number of these tetrahedra building blocks and how they are arranged into the 3 dimensions. And the dimensionality of these pores is also important, because as the sizes of the pores are very small, they can dictate like which molecules, or they approach the molecular size, so they can dictate like in how many dimensions the molecules of the substrates that we are using in catalysis can travel through the zeolite and through the pores. And the symmetry of the pores is also related to the 3-dimensional arrangement of the pores in space. And the exact chemical composition of the zeolites can vary, because they are usually aluminosilicates, and this change in chemical composition is very important and dictate a lot of their properties for applications in catalysis. Because even though we discussed so far that the building blocks are based on the tetrahedral unit containing silicium and 4 oxygen species, these silicium ions can also be replaced by other species that are small enough to favor this tetrahedral coordination. And one example is also aluminum. That's why they are aluminum silicates. They have a mixture of silicon ions and aluminum ions. So when aluminum ions replace the silicon ions in the structure, this leaves a negative charge on the framework, because they have like different charges, and these can be compensated by cations that are present inside the pores. And these can be protons or small alkaline or alkali earth species, such as sodium or lithium, for example. And these cations can be exchanged by other cations. So if they are exchanged by ammonia, for example, after subsequent heat treatment, we leave H+ ions present in the pores of the zeolite. They stay there to compensate the charge. And interestingly, these protons that become located in the micropores of the zeolite, they represent strong acid catalytic sites. And one of the important examples of zeolites in catalysis is the use of the zeolites as solid acids, because they can replace the use of zeolites, can replace the use of concentrated acidic solutions in a variety of acid catalyzed reactions. So the zeolite then has a lot of advantages relative to using concentrated acid solutions. So they were approached as being like solid acids, for example. And this is also important in other very In other examples of catalytic applications, for instance, for not only like using the zeolite to replace an acid in an acid catalytic reaction, but this has several other implications. So for the Fischer-Tropsch synthesis, for example, we have the active phase, which is like iron, cobalt species, for example, deposited over these microporous supports that can be zeolites as well, in which in one of the process of the Fischer-Tropsch reaction, CO is hydrogenated to CH species, and then the acid sites of the microporous silica or the acid sites of the zeolite, which is in the support, catalyzes oligomerization and growth of these hydrocarbon fragments into larger fragments. So this provides a bifunctional mechanism in the catalysis, in which the active phase can hydrogenate carbon monoxide, and then the strong acid catalytic sites in the zeolite catalyzes oligomerization, condensation, and isomerization reactions of these fragments, leading to the formation of larger hydrocarbons. So this is important in the context of the conversion of CO to hydrocarbons. So it's a bifunctional mechanism in which both the nanoparticle of the active phase at the surface of the support and the support provides catalytic active sites for the reaction to take place, and in this case, for different reactions during the catalytic cycle. So when we have, so this is an illustration of a two tetrahedra sharing a corner here, an oxygen ligand, in which we have a silicon and the aluminum species here. And then you can see that this, because of the differences in charge, this affects the acid strength, as we just discussed. So this acid strength that gives this strong acid behavior to the zeolites, this depends on several factors. So the acid strength will depend on the ratio between silicon and aluminum ions on the structure of the zeolite. So this acid strength can be controlled by controlling this ratio, and this ratio can be controlled by the synthesis. So the zeolites, they are usually combined with a metal function, as I discussed in the example here of the Fischer-Tropsch synthesis, for example, and then giving rise to a bifunctional catalyst. So these can be applied then in isomerization processes, hydrocracking transformations, and alkylation reactions. And the interesting part of using zeolites as supports is that they are easy to separate from the generated products during the nanocatalysis procedure. And therefore, they can also, their utilization can also prevent corrosion, for instance, of the reactors, as compared as if we had to use like strong acids instead of the zeolites. And an important characteristic is that the zeolites can also help to achieve more selective transformations, in which the selectivity can be dictated by the size of the micropores in the zeolite, because the size of the micropores are comparable to the sizes of molecules. So we can see here like two different molecules of substrate for example, that can undergo a specific molecular transformation. So we can see while this molecule is too large to travel through the pores of the zeolite, this molecule is small. So if we have either acid sites or metal species in the pores of the zeolite, these nanocatalysis can be employed to convert this molecule into something else, into another desired product, in which here you have selectivity, because only this molecule will be able to react as only this molecule can fit inside the pores of the zeolite. Another very important class of ordered microporous materials that have recently emerged and are very interesting. There has been a boom in the field of inorganic chemistry because of these materials and this class of important ordered micropore materials are the metal organic framework, also known as MOFs, which I am sure you guys have seen this. You guys have seen this already somewhere. So metal organic frameworks or MOFs represent ordered micro or mesoporous inorganic materials, and they have been known for quite some time. But the biggest problem with them is that usually they were unstable thermally. So the structure would break if we have higher temperatures. But in 1995, it was reported that like the use of dicarboxylate units to make these metal organic frameworks could lead to structures that were very stable and resistant to increases in temperature, for example, from the structural point of view. So this led to very structurally stable structures. And these structurally stable structures gave rise to a new class of materials at that time, and they were named as metal organic frameworks. And as opposite, on the contrary to zeolites, they do not occur naturally. They are only artificial materials. So metal organic frameworks, or the MOFs, they consist of metal ion complexes that are called as nodes. And these metal ion complexes or nodes are then connected by organic bridging ligands that are the linkers. So you have nodes that contain metal ion complexes, and these nodes are connected by organic bridging ligands that are the linkers. And this is organized into 3 dimensions, leading to a crystalline structure that also has pores. So the pores are defined by the crystalline structure that is obtained by the spatial arrangement of the nodes and the linkers. So one of the most well-known MOF or metal organic framework, and the only one that is produced on an industrial scale, is the MOF 5, in which the structure is shown here in this image. So here we have the structure of the zinc containing nodes of MOF 5. So here, the metal ion complex, here it's composed of zinc ions. So here is the structure of the zinc containing nodes. Here we have the primary unit cell geometry that is formed by connecting these nodes via benzene 1,4 dicarboxylic linkers. So here we have the linker. So the linkers having this dicarboxylic species connect which one of the nodes. So this is one unit cell for this structure, and this, when this is connected to many other building blocks into 3 dimensions, this leads to the formation of the metal organic framework structure, having the pores and channels as illustrated here. Okay, so here we have each one of these nodes, and here we have the linkers, for example. So these are the linkers, these are the nodes. And in this cubic symmetry of the unit cell, this leads to the formation of a cage here that has 1.2 nanometers in diameter. So in this case, it's a microporous structure with dimensions that can approach the size of molecules. And these are accessible via 0.48 nanometer entrances. So here we have 85.8 nanometer entrances. You see here this yellow sphere here is present to show the size of the pores inside the structure. So normally the nodes in the metal organic frameworks are composed of complex metals, usually zinc, copper, cobalt, nickel, and magnesium. Linkers are organic ligands, and they can also comprise nitrogen atoms. Some metal organic frameworks can be synthesized hydrothermally by heating the precursors in aqueous solution to induce the reactions that will generate the metal organic framework structure. But in this case, solvothermal synthesis, which is the same procedure by using non-aqueous solution, this is more common because of the organic linkers that are used. So generally, the growth of these structures or the crystals containing the metal organic frameworks occur from solutions containing metal precursor salts, such as nitrates or metal organic precursors, and also additional templates can be employed during the synthesis to further induce the porosity. But sometimes or often the solvent itself acts as a template. So here is an example of a formation of a metal organic framework in which we have the addition of the metal ions or precursors and the organic linkers during the synthesis, and the combination of the nodes and the linkers leads to the formation of the metal organic framework structure. So here is an example of an organic linker and a metal node, and the formation of the corresponding metal organic framework, in which we have the linkers, the inorganic complexes acting as a node, and here in yellow, just to show the dimensions of the pores in the structure. And here we also have another example. Here, other types of metal organic frameworks in which we can have different kinds of linkers for this node, for example. And one important difference, so here we have like an example of three classes of materials that we kind of covered here in our lecture. So we have MCM 41, which is a mesoporous silica, having this tubular structure, larger sizes. For example, we have the zeolite, which is a microporous material, and then we have the metal organic framework, which is also microporous. So here we have a comparison between zeolites, metal organic frameworks, and other mesoporous silicates and aluminosilicates. So in terms of crystallinity, zeolites and MOFs are crystalline, while these mesoporous silicates might not be. Zeolites and MOFs have homogeneous active sites as well, because the ions that are present, or the acid sites, or the ions in the nodes itself, they can have catalytic properties. In the mesoporous silicate, no. In terms of surface area, we can see that the metal organic frameworks provide the potential for very large surface areas. In terms of cavity size, for zeolites is usually below 1 or in the order of 1 nanometer. For metal organic frameworks, it can be controlled up to 4 nanometers, and for mesoporous silicate, it is usually higher than 2 nanometers. And then here, the diffusivity, which depends on cavity size, can be controlled for metal organic frameworks, while for zeolites are low, and for mesoporous silicate is high. And then we also have other comparisons in terms of stability and chemical versatility. And an important thing here is that for the metal organic framework, it has some advantage of both zeolites and mesoporous silicate, because we have a much higher degree of control, of synthetic control, in which the cavity size can be controlled into a larger window, into larger dimensions. We can have much higher surface areas, and the chemical versatility can also be very high. And here again, even the metals present in the nodes, the metal ions, can act as catalytic sites themselves, or also the metal organic framework can be employed as a substrate to deposit, to have the active phase on the surface. So supports for in nanocatalysis, having a bifunctional mechanism, or just to help selectivity and or just being the support. So their versatility is very high. So it's very, in terms of structure, it's very versatile. And also, I would like to show you some important images of this metal organic frameworks as well, that you can see also in this website, ChemTube 3D. So we can see here a variety of different metal organic frameworks. So here is the structure of MOF 5 that we just discussed here in the lecture. So interestingly, here is the structure of the material. So we can go around, check the nodes here, and then we also have the linkers here very clearly. We can show the pore size. We can show the size of the second pore. We can also show the channels present in the structure. So we can turn, we can see this very clearly. we can show the cavity fill. So a single cavity, look in here. So this is much better than my pictures in my slides. This becomes very clear. So we can show the zinc oxygen tetrahedra as well. We can either also, we can fly to the center of the pore as well to have a look at the pore structure. So here we see a linker, we are turning, we see another linker. Very nice. We can turn a little more, we can look up, we see here, we see there the node. So it's very nice. It's very interactive, it's very clear, it makes for a great, easy to understand. And here we have another type of metal organic framework in which we can do basically the same thing and interact with the structure in a very clear way. So I strongly recommend you guys to play around with this website and to understand better these structures and have a better visualization of things. Okay, so we will finish this metal organic frameworks discussion, and then we will stop for a break. Okay, so we are almost done. So interestingly, that like starting from these building blocks and by using the organic linkers, there is a lot of versatility in terms of structure and arrangements that can be performed. So we can change the pore size by using like different larger units as linkers, for example. And therefore the number of possible variations in the structure of metal organic frameworks is remarkable, and they are not limited to only tetrahedron building blocks, as in the case of zeolites. So structurally, metal organic frameworks are much richer relative to zeolites. And also a node can be connected to 2, 3, 4, or even 8 linkers in different geometric configurations, and the linkers can bridge 2 or more nodes, and giving almost an unlimited variety of structures, with even more than 10,000 metal organic frameworks being reported so far. And here we have some examples of some nodes and linkers, and that have been reported for metal organic frameworks. They are composed of like elements also, and therefore they can reach porous volumes of as high as 2 to 3 cubic centimeters per gram, very high surface areas, and in addition to catalysis, they have also been applied like for optical, magnetic applications, and separation. And their properties, the interesting properties of these metal organic frameworks, including the properties in nanocatalysis, can be from the metal organic framework itself, such as the metal ions in the nodes, or also due to guest species like nanoparticles deposited into the cages or the surface of the metal organic frameworks. And also recently, it has been reported zeolitic amidizolate frameworks, which are the ZIFs, which it's analogous to metal organic frameworks, but in this case, the organic linker is a imidazolate unit, which is a conjugated 5-ring comprising 2 nitrogen atoms. So in this case, we have a different kind of linker that it's employed in the ZIFs. So the ChemTube website also has the structure of some ZIFs structure that I also recommend you guys to check it out. So this imidazolate unit binds true transition metals, can bind two transition metals with a fixed bond angle that is close to the silicium, oxygen, silicium bonds in crystalline silica and zeolites. These zips also leads to the formation of framework structures which have pore symmetries, and these are very similar to what the pore symmetries and structures that are observed for silica and zeolites as well, because of the fact that these kind of the bond angles that are formed within the linkers and the nodes are similar to those observed for silica and zeolites. And the thermal and chemical stability of these ZIFs are even better relative to the MOFs. And the ZIFs, as discussed by the MOFs, they're based on metal complexes acting as nodes, and the zeolitic imidazolate species as being the linkers. So here's an example of a node connecting to different kinds of linkers, generating the ZIF structures. And here's another representation of a ZIF structure. And then by choosing different linkers, we can tune and change and control the pore and the cage size, leading to a lot of structural variety. And also these materials can be employed as substrate or as support for the deposition of catalytic nanoparticles, for example, generating nanocatalysts. So here we have the synthesis of this ZIF 67 that was obtained here by the mixture of a cobalt precursor with the linker, right? And then this was treated under this condition. This led to the formation of this ZIF structure, and then gold nanoparticles were deposited onto these structures, generating, as we see here, the nanocatalyst containing gold as the active phase and the ZIF structure as the support. So here the brighter regions comprise the gold nanoparticles, and the less bright areas are the ZIF supports. And this is another example of a palladium nanoparticle actually inside the pores or inside the ZIF framework structure, in which the palladium nanoparticle here is then kind of protected by the ZIF structure surrounding these nanoparticles, acting as the support. This makes the nanoparticle to be like water compatible and in a kind of a protected reacting chamber. So the support, as it's porous, enables molecules to come in and out. So it's like the nanoparticle is inside a reaction chamber, and the ZIF structure here control the flow of reactants that can interact with the nanoparticle. And this system specifically is biocompatible. So this kind of nanoparticle has been employed for nanocatalysis inside cells, for example, in this work. And here is another representation of different ZIF structures, in which here in yellow we have the illustration of the different porous sizes. Okay, so let's stop here for a quick break. So it's 1:13 now. So we come back at 1:28, okay? All right, so I will see you guys again at 1:28. See you. Hello, everybody. So welcome back to our second half of our class today. So after the discussion of these support materials so far, which were the disordered solids, mesoporous silica, then zeolites, metal organic frameworks, MOFs, and then the ZIFs, which are also uh, microporous organized framework structures. Another class of important supports that are employed in nanocatalysis are carbon materials. So porous carbon materials, they are very interesting for nanocatalysis applications to be used as supports because they can be available in a wide range of morphologies, purities, and a wide range of costs. And some of these are very cheap, which is very interesting for practical industrial applications, for example. So we have activated carbons, carbon aerogels, carbon black, carbon nanotubes, carbide derived carbons, templated carbons with different surface areas, porosities in terms of purity and prices. So we can see that the activated carbons and carbon black are very low on price, and because of that, they are widely used, and they are widely used in electrocatalysis applications as well, which we will cover later in this course, because for electrocatalysis, we also need a support that has conductivity. So carbon black meets this criteria. So the most regarding the carbon materials in nanocatalysis, the most widely applied are the activated carbons because they are cost effective while having a high specific surface area. They can be produced from natural byproducts such as wood, bones, among others. So these natural byproducts are heated up to high temperatures ranging from 800 to 1,500 degrees C, and this like leads to the formation of carbons. Then, of course, this is under controlled atmosphere, and subsequently, this material is subjected to an activation treatment, and the goal of this activation step is to induce extra porosity. And one example is leaching with a strong base, such as potassium hydroxide or an acid or a steam treatment or a combination of both. So this activation induces extra porosity. So this is the goal of this activation step. So here we have a transmission electron microscope image of some nickel cerium nanoparticles deposited over an activated carbon support. So these activated carbons, they are mostly microporous, so they are not they are not ordered materials, but they can also be meso or microporous, depending on the nature of the carbon that is employed, as we saw in the table two slides ago. And they can have high specific surface areas. And what makes them ideal is this combination of high specific surface area and easy of synthesis and low cost. So here is an example then of these dispersed nanoparticles over a carbon support being employed as catalysts for the reaction from the reaction that generates carbon dioxide and hydrogen from carbon monoxide and water. So all these supports that we discussed so far, they have nanometric features in the case of the microportal supports, but they also, like regarding the particle size, the overall particles are mostly in the micrometer size. So they are typically consist of fine micrometer sized powders. However, when we want to go to a larger scale, the handling of these powders and the packing them into like meter-sized reactors in industry that uses meter-sized reactors, this is not possible, this is troublesome, because this would lead, for example, to handling limitations, pressure drops, or difficulties separating the catalyst from the gas or liquid stream. So in practice, for industrial application, these micro or mesoporous particles, they are usually shaped into macroscopic bodies. So here we are discussing the shaping of these support materials or support materials containing the active phase as well. And then this shaping uses, for example, additional binders, fillers, or other additives. And it's usually produced pellets by pasteurization or extrudates by extrusion. And these are subsequently packed into industrial reactors for applications, as we see here, in which we can have like these pellets having the shaped catalyst particles, and these can then be packed into a fixed bed reactor of meter-sized dimensions in industry. So the active phase is microscopic, the support containing the active phase can be like mesoscopic, and then the final catalyst for industrial applications have macroscopic dimensions. So here are some of the overview of the common techniques that are used to shape the supports or the nanocatalysts into larger bodies or macroscopic bodies for industrial applications. So here are some of the techniques and the typical sizes that are obtained by each one of these techniques, and what kind of reactors each one of these shaped nanocatalysts and supports containing the active phase are used for industrial applications. Okay, so in this section, we mostly covered only like the synthesis of the support materials, because these supports play an important role in the synthesis of nanocatalysts. But now let's take a look at the overall nanocatalyst. So the nanocatalyst having the active phase deposited over the support. So let's take a look not only on the support, but let's take a look on how we can prepare the supported nanocatalyst. So in this case, how can we deposit, or how can we synthesize, and how we can synthesize and support the nanoparticles of the active phase at the surface of our support materials that are usually employed in catalysis. So now we will shift our attention from the support. Now we will move to the nanoparticles of the active phase that will be deposited over the support. So let's shift our attention now to the synthesis of the supported nanocatalysts. So remembering here, so that the catalyst has the support, the nanoparticles of the active phase, and then these can be shaped into larger bodies as we have just seen it. So now we will focus on the synthesis of the nanoparticles that are the active phase supported onto the different kinds of supports. So the synthesis of the supported catalyst So, or the supported nanocatalyst. So when I'm talking about the supported nanocatalyst, nanoparticles of the active phase, which can be often a metal nanoparticle, deposited over the surface of the support material. So the synthesis of the nanocatalyst, the supported nanocatalyst, aims at fully controlling the properties of the active phase and therefore the properties of the nanoparticles. And these properties of the nanoparticles and therefore the properties of the nanocatalyst, catalytic properties, are determined by several different factors or several physical and chemical parameters that define the nanoparticles of the active phase, such as the composition, the size, the shape that changes the nature of the exposed facets, or the geometric effect, or the atomic arrangement at the surface, and the coordination numbers, and the interaction of this active phase with the support. So these factors influence the properties of the final nanocatalyst that we are using. And interestingly, the catalytic properties of a nanocatalyst depends then on several factors or several physical and chemical features of the nanoparticles that contain or define these nanocatalysts, such as size of the nanoparticles, the shape of the nanoparticles. So the size will influence the number of exposed active sites, as well as coordination numbers, in which the coordination number will decrease with the decrease in size, and this will influence the bonding with substrate and intermediate, and this will dictate activities, as we have seen in the course already. So shape will change the nature of the exposed facets at the surface, so different atomic arrangements, so different coordination numbers as well at the surface, different compositions, different structures, metal support interactions. So developing strategies for the controlling these parameters, these physical and chemical parameters during the synthesis of a nanocatalyst is important for the optimization of nanocatalytic performance, and also to understand or to establish structure performance relationships in which we can understand how nanocatalytic performances depend on several of these parameters that define our nanocatalyst. So in addition to the individual properties of the nanoparticles present in our nanocatalyst, the collective properties of an ensemble of nanoparticles deposited over the support is also relevant. So, for example, the spatial distribution of nanoparticles over the support is interesting and important because we desire an important distribution of nanoparticles over the support. That's what we desire, right? So in order to maximize the surface area or the exposure of catalytic active sites, we have to have like interparticle spacing, so a uniform distribution of nanoparticles over the support without agglomeration. And the interparticle spacing is also important in terms of to avoid loss of activity due to the particle growth via processes such as migration of particles and coalescence, or via Oswald ripening. Because, for example, if the particles are too close to each other in the support, process such as coalescence, in which particles migrate and then they combine to generate a larger nanoparticle, this is more easy to take place, and this is a thermodynamically favored product, because if we generate a larger nanoparticle, this leads to an overall decrease in surface area. So this would be thermodynamically driven. And the same for oswald ripening, in which is a process in which larger structures grow at the expense of smaller ones. And this is also driven thermodynamically, as the growth of the larger particles at the expense of the smaller particles is also thermodynamically driven, because the product has a lower surface area and therefore lower surface energy. So these processes lead to the growth of the nanoparticles present on the support, and therefore this leads to the decrease in the catalytic properties. So therefore this should be avoided as much as possible. And the interparticle distance can influence this process to occur or not. So these are the requirements of a successful catalyst that we have discussed as well a few times during this course. So we want high activity per unit volume, high selectivity, long lifetime, which means stability, possible to regenerate, easy to prepare, and stable against sintering, structural changes, or other changes during the reaction conditions. And here are some examples of different kinds of changes that can occur for a catalyst containing a nanoparticle deposited over the support during the catalyst. So a variety of processes can take place that leads to the decrease in catalytic activity. So it's important that we have stability and avoid processes such as dissolution of the nanoparticles or leaching of the nanoparticles from the support, the sintering, which means like that occurs as a result of coalescence. So we have a decrease in surface area, the formation of complexes at the surface that can be leached as well. And then these complexes, for example, can block catalytic active sites, surface segregation, so a change in the surface of the nanoparticles that also can lead to the loss of activity, a change in the phase, a change in the morphology to a morphology that is less active, or the formation of a composite or a new phase here due to the interaction of the nanoparticles in the support that becomes less active towards the transformation of interest. So regarding the synthesis of the supported nanocatalyst, or the active phase deposited over the surface of the support, there are two main methods for the synthesis of the nanocatalyst or the supported nanocatalyst. The first one is the cryoprecipitation of both the support and the catalytic active component. So in the same step, we make the synthesis of the support and the synthesis of the nanoparticles together, and then the end product will be the nanoparticles supported onto the support material. So this gives a mixture that is subsequently dried, calcined, and then reduced to yield a porous material with a high surface area containing the nanoparticles of the active phase. So this is the first approach. The second approach is to have the preformed, is to make the support first, and then loading the support material to the reaction mixture. And then in this case, the active phase or the nanoparticles of the active phase are loaded into the pre-existing support by methods such as impregnation or precipitation from solution. And this is, for example, the preferred method when the catalyst precursors are expensive, and the aim is to have very well-controlled nanoparticles, or to deposit very well-controlled nanoparticles at the surface of the support. So the first one, in the first method, we make the support and the nanoparticles at the same time. And in the other method, we make the support first, and then we use the support and then we load into the support either the preformed nanoparticles or the precursors to the formation of the nanoparticle, in which the nanoparticles are then formed at the surface of the support material in a separate step. Okay, so we have several different strategies for the synthesis of these supported nanocatalysts. So we have colloidal synthesis, and then here we have a comparison of the different synthesis methods regarding the metal loading that can be achieved, the metal dispersion that can be achieved, the advantages and the challenges of each method. So the colloidal synthesis regards like making the nanoparticles first and then loading the nanoparticle into the support. So this enables a low to medium metal loading over the support with a medium metal dispersion. The advantage is that we can then control precisely the size and the shape of the nanoparticle. And one of the challenges here is the effective anchoring of these nanoparticles over the support. Other strategies such as chemical vapor deposition, for example, provides also low metal loading, a monolayer metal dispersion, has the advantage of monolayer control, but the challenge is that special large equipment are needed. Other methods that are simpler, such as ion adsorption, deposition precipitation, and co-precipitation, and impregnation and drying. They have other features, but they have, for example, ion adsorption has the advantage that provides atomic dispersion, but we can observe gradients over the support. And then for deposition precipitation, it has limited applicability. Co-precipitation is challenging in terms of catalyst activation, but it's interesting because we can get very high metal loadings and impregnation and drying. This is widely applicable. This is a nice advantage, but the reproducibility is one of the main challenges. So there is no, it seems that there is no perfect method, and each method has an associated challenge within. So all these methods that I mentioned in the table in the previous slides, they are widely used in research, so in academia. But regarding industrial examples, only co-precipitation and impregnation and drying are applied. So co-precipitation, both support and nanoparticles formed together, and impregnation and drying. So these are the only methods applied in industry. The other methods, such as the colloidal synthesis, chemical vapor deposition, and deposition, precipitation, and ion adsorption, are not extensively used in industry in the context of catalysis. And this is because of usually high precursor costs. They can generate large amounts of waste gas or waste water, and it can be relatively complex in operation. And this is particularly important for chemical vapor deposition techniques that usually needs some special equipment. So the plan is to discuss all these types of methods and to describe all this kind of methods of synthesis of nanocatalysts to you guys. So firstly, I will talk about the colloidal synthesis, which consists in making the nanoparticles first and then impregnating these nanoparticles onto the support. So the colloidal synthesis is very interesting because we can have a control over the size and shape of the nanoparticles prior to loading them into the support materials. For example, even though the synthesis of gold nanoparticles was described a long time ago by Faraday, for example, for many decades. Recently, there has been significant progress in the synthesis of not only gold, but a variety of different metal nanoparticles that enable their shape and control synthesis, therefore allow accurate control over nanoparticle morphologies. And these methods for the synthesis of metal nanoparticles that comprise colloidal synthesis, they usually start from a homogeneous solution containing the precursor that via reactions of decomposition, of reduction, leads to the growth species containing the metal that will originate the metal nanoparticle, and by combination of nucleation and growth processes, the nanoparticle is formed. So we will talk about the synthesis of nanoparticles briefly here in our course, in which we will discuss how the colloidal synthesis can be employed to the synthesis of these metal nanoparticles that are important in nanocatalysis. So you will briefly discuss the fundamentals of homogeneous nucleation, growth, how to get monodispersed size and control shapes, which are important for nanocatalysis, and we use the example of silver as a representative example on shape control, for illustration. Yeah. Okay, one important thing when we talk about the colloidal synthesis of metal nanoparticles is that the synthesis must overcome the high surface energy, because nanoparticles have small sizes, and as a result of their small sizes, they have high surface energy. So high surface energy means that the system is thermodynamically driven to reduce surface energy to increase stability. So the synthesis methods must overcome this surface energy to avoid nanoparticle aggregation. So this is, for example, the variation in surface energy as a function of nanoparticle size. So you can see that when we go from centimeter to nanometer dimensions, there is a marked increase in surface area, which is followed by a high increase by several orders of magnitude into the surface energy. And the surface energy in nanomaterials comes from the fact that atoms at the surface of a nanoparticle have lower coordination numbers relative to atoms in the interior of the nanoparticles. So here we have missing bonds, lower coordination numbers, right? So this is what gives origin to the surface energy of a surface. So surface energy, I'm sorry, here there was a mistake. So it's the surface energy, it can be defined as the extra energy that comes from the surface atoms as a result of the lower coordination number. But from physical chemistry, surface energy can be defined as the energy required to produce a unit area of a new surface. So this relates to the number of broken bonds that are related to create the new surface, the bond strength, and the surface atomic density. So because of that, I'm sorry, here there was a mistake there was something wrong with the PowerPoint. Here you correct this to post it for you. So for FCC metals, we can see that the different surface facets or the different crystallographic dimensions, 100, 110, or 111, these have a different packing of atoms or a different arrangement of atoms at the surface, and therefore the surface energy of these different types of surfaces are different. And this is what makes this is important during the synthesis to control their shapes, and the control over shapes, because the surface energy is different. We also the surface energy is different because of the difference in the atomic arrangement and the coordination numbers. But this also is important not only to control the shape and the synthesis of the nanoparticles here, for example, for palladium, but this also influences catalytic activity. So here is the activity for oxygen reduction reaction, for example, because we can see that the different, and we have seen already in the course that the different surface exposure gives to different atomic arrangements and different coordination numbers, and this changes the D-band center of the materials, and therefore this changes catalytic activity, or this influences catalytic activity. So this is very important, not only from the synthesis part, but also to control or to tune catalytic activities as well. And then we have to overcome these processes for the synthesis of nanoparticles. We have to overcome processes that would lead to the minimization of surface energy, such as aggregation by coalescence or Ostwald ripening, as a for support the nanoparticles. Also, during the synthesis of nanoparticles, it's important to avoid these processes that lead to the growth and reduction of surface area and therefore surface energy, so that we can have the synthesis of well-defined nanoparticles. Okay, so let's stop here from now. So our next class will be only after the Easter break. So the idea is we will finish our discussion on synthesis of supported nanocatalysts. Then we will discuss photocatalysis, electrocatalysis, characterization of nanocatalysts, and then we will have the student seminar. Then we will have the discussion on kinetics in catalysis, and then we will go over the student seminars. Okay, so later today, I will post homework for you guys, and I will also post the materials of this lecture. So does anybody have any questions before we wrap up? If not, thank you very much for being here with me. I will see you guys in the next lecture, which is on April 8th, I believe. So have a nice rest of the week and have a nice Easter break. Thank you very much.
Yeah, thank you.
Thank you.
How about homework? Like you said you would discuss something.
About what? Say it again, please. I didn't.
About homework.
Oh yeah, I will include a homework. I will add a homework today for you guys on Moodle.
Okay, yeah.
Yeah, and then I will send an email reminder when I post the homework. That's it, yeah.
Okay, yeah. Okay? Thank you.
All right. Bye-bye, everyone.
Bye.
Bye-bye. Happy Easter.
Bye.